Hi everyone, welcome back. So this time we got a group problem. So grab a friend, grab a rubber duck, and we'll do it together. I'm serious about the rubber duck thing. It actually works. Just try explaining your problems to some inanimate object and you'll find out that you can figure out your errors a lot more often than you think. So what do we have? Well, we have a solid brass axis member and it's loaded and supported as shown over here. Now segments 1 and 2 have a diameter of 25 millimeters, while segment 3 has a diameter of 14 millimeters. They're loaded as shown, however, this is a typo. It should be 28 kilonewtons right there. So what do we want to know? We want to know the deformation of segment 2, we want to know the deflection of point D, and we want to know the maximum normal stress inside of the entire axis member. So let's try it out. We're going to calculate the internal force in section 2 first. Now, in section 2, if you remember, go back to it right here. If we cut straight through this guy, we're left with, we'll get rid of the top. We have to have a force now. It's going to have to be the same as 14 kilonewtons and 28 kilonewtons. 14 and 28. Okay, now that goes to be 42 kilonewtons. Now you might be asking yourself a question here. Why did I keep the bottom and not the top? Because there's only one force up here. Why didn't I say like, okay, well, I'm gonna get rid of this and I only have this one force, that's 40 kilonewtons. Wait a minute, that's 40 kilonewtons. What's going on here? You see 40 kilonewtons being applied. What you're forgetting maybe is that there is a reaction force up here that we haven't calculated. So that reaction force is what keeping this all in equilibrium, keeping it stable. And so since we don't know that and don't really feel like calculating it yet, that's why we keep the bottom. Now with this we can calculate the deformation in section 2, which is going to be 42,000 kilonewtons times 1200 millimeters over 490.8739 millimeters squared, which is the area. We get that from our area is equal to pi over 4 times the diameter squared. And multiplying this by 100,000 newtons per millimeter squared, which is the elasticity. When we do that, we get our 1.027 millimeters. That's how much is elongated. Now, what's the internal force in section 1? Well, if we cut it, we'll see that there's 3 forces all pulling down on it. 40 kilonewtons, 14 kilonewtons, and 28 kilonewtons. And that has to equal 0, therefore there is an internal force of 82 kilonewtons within force 1. I'm just guessing here, but that's pretty big. It might be the one with the highest normal stress. Now let's calculate the deformation of section 1, because we're going to need all the deformation to figure out how far the bottom moved. So we plug it into our equation. We have the load, 82,000 newtons. We have our length, 1,800 millimeters. We have the area, which is the same as last time. That's just coming from pi over 4 times the diameter squared. And we have our elasticity. It comes out to be 3.007 millimeters deformation. Now, you didn't think we were going to get to leave section 3. Now we got to mess with it too. So there's only one load if you look at it from the bottom. Pull it over here. Whoop. Right there, if we cut it right here, we don't see any of the top anymore. We have that 28 kilonewton load. And there we are. So force 3 is going to be 28 kilonewtons, and we calculate the deformation, which we plug all of our equations into. Plug the force, we plug the length, the elasticity, and our area. The area was different this time because it's pi over 4d squared, and d was equal to 14 millimeters this time. And I get 2.810 millimeters. Whoop. So with this, we have the total elongation of our section. And by adding all these together, we can figure out how much the bottom moved. The one thing we haven't done here is determine which one has the maximum normal stress. Which one has the maximum normal stress? Now, this isn't too terribly difficult. We already figured out that this one has 42 kilonewtons. This one has 82 kilonewtons. Since they have the same area, this one's going to be it. This will not be it. And then the second question is, well, is this going to have maximum normal stress or is the top one? So Let's look at it and see. So we have 28 kilonewtons over an area of, I believe it was 146 millimeters squared, somewhere around there. And we have 82 kilonewtons over an area of, I'll go ahead and move over here so I can see it. It was 490. Millimeters squared. Plug these into our calculator. What do we get? We get 28 divided by 146. It's going to be 0.191 megapascals. And 82 divided by 490 is going to be 0.167 megapascals. So from this we can see that section 3 will have the highest stress at 0.191 megapascals. So, or 191 kilopascals. So with that, thank you for listening. I hope this helps you see how you work through these problems, how you go from one step to another, and how you can use these equations to help you solve for the elongation of a compound system of bars. Have a wonderful day. Bye-bye.